An operational amplifier is an IC device used to amplify the potential difference between the signals applied to its input terminals. For that reason, operational amplifiers are also referred to as differential amplifiers. Hello everyone, welcome to my channel. My name is Rafael. I am an electrical engineer, and in this video I would like to invite you for a debate about operational amplifiers through 7 exercises that frequently appear in exams for electrical and electronics engineers. Let's go to the first exercise. Exercise number 1. What is the output voltage of the amplification circuit if the op amps are ideal? So we have this amplification circuit, and the exercise is informing us that the operational amplifiers are ideal. Okay? So this is the exercise. Let's go to the solution, my friends. The voltage between points A and B, take a look at them. The voltage between points A and B can be found by applying superposition in the first op amp. Let's consider the first op amp first. We are going to set each of the voltages here, 5 volts and 2 volts, at rest, and the resulting voltage is going to be the result of superposition applied to the first operational amplifier. Okay, so this is what we are going to do to find this voltage here. It is the first step in solving this problem. First of all, when the 2-volt source is at rest. Okay? When this is at rest, a voltage source at rest is a short circuit. Then we have a short circuit to ground here, okay? This terminal here is ground and this is at rest. Then we have ground here. Then VAB1, okay, is equal to negative R2 over R1 times 5 volts, okay? Why this? Because we are connecting this source here at the inverting terminal, okay? And the gain of the inverting configuration is this, where 2 ohms is R2 and the resistor R1 is 1 ohms, okay? Then VAB when 2 volts is at rest is this. VAB1 is negative R2 over I1 times 5 volts, which is equal, we just substitute the values, negative 2 ohms over 1 ohm times 5 volts, and this is equal to negative 10 volts. Okay, now we are going to put this voltage here at rest, and this is going to be a short circuit, okay, to ground, and this voltage source here is on, okay, and this is off. When the 5-volt source is at rest, When this is at rest, we connect the voltage to the non-inverting terminal, okay? Then we are going to have the gain for the non-inverting configuration. VAB2 is equal to 1 plus R2 over R1 times 2 volts. And if we substitute, remember that this is R2 and this is R1. And when we substitute, we find 1 plus 2 ohms divided by 1 ohm times 2 volts, and this is equal to 6 volts. All right? And the superposition principle says that we can sum them, and when both are on, they participate together simultaneously, then the voltage here is going to be obtained from the sum of the individual contributions, okay? Then VAB is equal to negative 10 volts plus 6 volts, and this is equal to negative 4 volts, okay? Now we know the voltage between points A and B. With this result, we can calculate the output voltage. Now, we are interested in VO, the output voltage. And this last result, VAB, enables us to calculate VO. Observe here that the signal goes to the positive terminal, to the non-inverting terminal. Then we can affirm that this second operational amplifier is connected in the non-inverting configuration, and thus the output voltage is VO is equal to 1 plus R4 over R3 times this voltage here that we found, VAB. And here we are considering that this is R4 and this is R3, okay? When we have such a configuration, okay, to ground here and the signal entering through the non-inverting terminal, then we have this kind of gain here. And using the values, 1 plus 4 ohms divided by 1 ohms times negative 4 volts, we find negative 20 volts, okay? And this is the output voltage, negative 20 volts. All right, my friends. And this is all for exercise 1. Let's go to exercise 2. Exercise number 2 now. Calculate the output of the circuit if the op-amp is ideal. Okay, my friends, this is the question. Let's go to the solution. As we did before in exercise 1, here we are going to apply superposition. The output voltage will be obtained by applying superposition, setting each of the voltage sources at rest one at a time, okay? This is the circuit symbol that we use when solving exercises and understanding the theory. And this is the actual 741, which is a practical and commercially available operational amplifier, okay? This is exactly the same as this, okay? So, firstly, we understand this, which is easier, and then we move on to this, all right? Okay, setting this 4 volts voltage source at rest and only working with this 10 volts voltage source, the output voltage is now. We are going to set this voltage source at rest and work only with this voltage source. But observe that the polarity here is inverted. We are not connecting the positive terminal of the battery to the positive terminal of the operational amplifier. We are connecting the negative terminal of the battery to the positive terminal of the operational amplifier. Then the output voltage, when only this is on and this is off, is okay, and this is gonna be the output voltage. Okay. Forty divided by 80 is a half, negative a half times 10, negative 5. 40 divided by 80 is a positive half plus 1.5 times negative 4, it's negative 6. And this is negative 11 volts. And this is the solution of this exercise. But before we move on to exercise 3, let's understand something here. What if we invert the polarities here? What if we do it, instead of putting it in this way, we change it to this. Positive here and negative here, okay? We are applying positive voltages here. This to the negative terminal and this to the positive terminal. What would happen? If we do this, the output voltage will be, this stays the same, okay? But this will be positive because now we are applying a positive voltage here. Then here it is going to be negative 5 volts plus positive 6 volts. And this is 1 volt. And what is the conclusion that we get when we change the polarity here or here? Okay, we see that when they have the same polarity here as this example, both positive terminals of the battery applied to the input terminals of the operational amplifier, the output is going to be the difference. Okay? Then we are implementing a difference amplifier, but if we change the polarity here, instead we are going to have, instead of the difference, we are going to have the addition, okay? The addition, and this addition is going to be amplified according to the values of the resistors that make the feedback loop around the operational amplifier. Okay, my friends, and this is all for exercise 2. Let's go to exercise 3 now. Exercise number 3. What is the output voltage of the following amplification circuit? And this is the circuit that we are going to work on now. Let's go to the solution, my friends. Observe Observe that the signal is entering through the non-inverting terminal here, okay? But take a closer look. Observe that the voltage of the source is not directly applied to the non-inverting terminal of the op amp. Okay? To obtain the correct voltage at the plus terminal, we need to apply the voltage divider rule. Okay? We do not want this voltage here because it is not being directly applied here. We want the voltage from here to ground. Okay? And to do this, we need to apply the voltage divider rule here. So V plus is equal to, okay, the voltage is going to be here. So we are going to take this as a reference. It is going to be 20 ohms divided by this plus this, 20 plus 20 times the voltage. But here observe that the voltage is downwards instead of upwards. Then it is going to be negative 2 volts. Okay? Could you guys understand? And if we carry out, we find that it is negative 1 volts. Alright? So, it is not 2 volts that is being applied here. It is negative 1 volts. Now that we already have this, we can calculate VO. And remember that we are dealing with the non-inverting configuration. Okay? And it is going to be, then VO is going to be 1 plus this divided by this. 200 ohms divided by 50 ohms times the signal applied here. We calculated it and we found negative 1 volts. And calculating, we find ultimately that VO is negative 5 volts. Okay? Very simple exercise, isn't it, my friend? Just to practice speaking about and understanding circuits containing operational amplifiers. And it is all for exercise 3. Let's go to exercise 4 now. Exercise number 4 now. For the circuit of the figure, draw the output waveform and calculate the output voltage at t equal to 25 milliseconds. Okay? This is the circuit that we are going to work with. And observe here that I drew the circuit around the 741, which is a practical operational amplifier. Observe also that pin 2 is the inverting input terminal. Pin 3 is the non-inverting input terminal. Pin 4 is the negative supply. Pin 7 is the positive supply. And pin 6 is the output terminal. Okay? Let's go to the solution. Observe that the amplifier is connected in the non-inverting configuration. The signal is entering through the positive terminal. Okay? Then the gain will be 1 plus R2 over R1. Where is R2? R2 is here. And R1 is here. Okay? This is the gain of the non-inverting configuration, and using the values, V out of T is equal to 1 plus 1 ohm over 1 ohm times V in of T. Okay? 1 divided by 1 is 1, plus 1 is 2. Then V out is equal to 2 times V in of T. And the exercise stated that V in is this. Then for us here, V out will be to 10 times the sine 60 pi t plus 28 degrees. And this is voltage. All right. Now let's draw the exercise wanted us to draw. Let's draw here. Okay. The first thing that we notice is that we are limited by the external power supplies, okay, connected to pins 4 and 7, okay. Then, as our DC supplies provide only 8 volts, we are not going to reach 10, okay? We are going to stop at 8. So this is going to be the output waveform. Okay, the output waveform is this. It is not a perfect sinusoid because we are limited by the DC power supplies. We are not going to reach 10. We are going to be limited by the 8 voltage power supplies. Okay? Observe that the maximum output voltage supplied by the sources is 8 volts in magnitude. Therefore, the waveform will be clipped off at plus minus 8 volts and will not reach the peak of plus minus 10 volts, okay? And this is the clipped off output waveform. We are not going to reach 10. The waveform is going to be clipped off at positive and negative 8 volts. All right. Now let's respond to the other question. The exercise wants us to evaluate the output voltage at t equal to 0.025 seconds. Or if you prefer, 25 milliseconds. At 0.025 seconds, the output voltage will be, let's simply use this value here, okay? V out of t when t is equal to 25 milliseconds is equal to 10 times the sine of 60 pi, but we have to convert from radians to degrees because the phase was given in degrees. Then we are going to convert using this conversion factor here, 360 degrees for 2 pi radians times 0.025 seconds plus 28 degrees, okay? And carrying out this, observe that this is a multiplication and this is an addition. We find that the output voltage is negative 8.83 volts. But there is a catch here. We do not have this voltage, okay? We stop at negative 8. The waveform is clipped off. As we saw, the voltage cannot exceed negative 8 volts. Thus, at t equal to 25 milliseconds, the voltage will be negative 8 volts. So instead of this, the voltage is actually 8 volts. Okay? Beautiful, isn't it? And my friends, this is all for exercise 4. Let's go to exercise 5. Exercise number 5. During testing of an operational amplifier, signals of equal magnitude and opposite signs are applied to the two input terminals of the device. In this case, what kind of gain is being measured? Okay, my friends, this is the exercise. Let's go to the solution. Two signals are being applied to the input terminals of an operational amplifier. But observe that although they are equal in magnitude, okay, the exercises say that they are equal in magnitude, but the signs are opposite to each other, okay? The exercise stated that V1 is the negative of V2, but that their magnitudes is equal. Observe that by definition, the differential amplifier will amplify the difference in voltage, okay? VID is equal to V2 minus V1. This is the difference between the input voltages. And if V1 is equal to negative V2, then VID will be equal to V2 plus V2, which is equal to 2 V2. And nevertheless, real and non-ideal amplifiers also have a common mode amplification. In this case, VICM is equal to V1 plus V2 divided by 2. This is the definition of the common mode voltage, which is also amplified by real, in other words, non-ideal op amps. Ideally, operational amplifiers only amplify the difference between the signals applied at the input terminals, but real amplifiers also have common mode voltage amplification, okay? And since V1 is the negative of V2, we use that V1 plus negative V1 divided by 2 is equal to 0. Okay? If they are perfectly equal in magnitude but opposite in sign, then we are rejecting common mode signals and we are amplifying only the difference. What is the conclusion that we get from this? Consequently, only the difference is being amplified, okay? And thus only the differential gain is being measured. Then from this result here, we conclude that only the differential gain is being measured. The common mode gain is not being measured when we have such a configuration. Okay, my friends, and this is all for exercise 5. Let's go to exercise 6 now. Exercise number 6. In a real op-amp, if the voltage with respect to ground of the inverting terminal is 1 millivolts and that of the non-inverting terminal is 2 millivolts, and if the output voltage is 10.01 volts and the gain 10,000, what is the common mode rejection ratio? Alright, my friends, this is the exercise. Let's go to the solution. Observe that by definition, the differential input voltage is VID is equal to V plus minus V minus, which is equal to 2 millivolts minus 1 millivolt, which is equal to 1 millivolts. Okay? Similarly, notice that the common mode input voltage is given by V plus V minus divided by 2. Okay? And in this case, the common mode input voltage is 2 millivolts plus 1 millivolt divided by 2, which is 1.5 millivolts. For a real, in other words, non-ideal op-amp, the output is given in terms of the differential and the common mode gains. Alright? We are not talking about ideal amplifiers anymore. For ideal amplifiers, we do not have the common mode signal, only the differential signal, okay? We do not have common mode amplification, only the differential amplification. But in real amplifiers, common mode signals will be amplified. And the output voltage is therefore VO is equal to AID times VID plus AICM times VICM. Rearranging these terms, we get that AICM, okay, is equal to VO minus AID times VID and it all divided by VICM. And the output voltage in this case was stated to be 10.01 volts. The differential gain is 10,000. And the differential input voltage 1 millivolts. And it is going to be divided by VID. VID here, we discover it as 1.5 millivolts. And consequently, the common mode gain is 6.67, okay? Finally, to calculate the common mode rejection ratio in decibels, we use the following expression, okay? CM R, the common mode rejection ratio in decibels, is equal to 20 times the logarithm of AID divided by AICM. Okay? AID was given as 10,000. And the AICM, we calculated it and we discovered that it is 6.67. And ultimately, we find that the common mode rejection ratio is 63.5 decibels. Okay, my friends? And this is all the exercise wanted us to calculate. And it is all for exercise 6. Let's go to the last. Let's go to exercise 7. Let's go to the last exercise, exercise number 7. Design the instrumentation amplifier of the figure to provide a gain that can be varied over the range of 2 to 1,000, utilizing a 100 kilo ohms variable resistance. Okay? Before making use of the variable resistance, we are going to put the variable resistance here in the place of R1. But before doing this, we are going to understand the instrumentation amplifier, such as this one. And let's understand it when R1 is fixed. The exercise wants us to use a variable resistance here, but it is going to be useful if we understand first when this resistance is fixed. Observe that VID equal to VI2 minus VI1 appears across the resistor R1. How? Let's suppose that these two operational amplifiers are ideal. If this is the case, then the voltage here will appear here, okay? Because there is a virtual short circuit here, and here as well, okay? Then this voltage is going to appear here, and this voltage is going to appear here, alright? The current flowing through R1 is, there's going to be a current here. This current here I, and the value of this current is, the value of I is VID divided by R1. we have here VID. Okay, because we have understood that this voltage is going to appear here and this voltage is going to appear here. Then the voltage across the resistor R1 is VID. Voltage divided by resistance is current. Then this current here is the current that flows here, okay? The potential difference follows the path of current. The potential difference here follows the path of current. Then we can say that VO2 is equal to, the voltage here is going to be equal to the voltage drop here, plus the voltage drop here, plus the voltage drop here, plus this voltage here. And the voltage drop here is R2 times VID over R1, okay? The voltage drop here is the product between the resistance and the current. We have already understood that the current is this, okay? Plus the voltage across the resistor R1. We have already understood that this voltage is VID, okay? VI2 minus VI1. VID. Plus the voltage drop across this resistor here, which is the same as the voltage drop that we found for this resistor here. R2 times VID divided by R1 plus the voltage here, VO1. We are assuming that this is higher in potential than this, okay? Then this plus this plus this plus this is equal to this, okay? It's just you have just what's just your sight on this, how you understand this, because frequently when we are analyzing circuits, what is below is lower in potential than what is above. But here in our circuit, this below is higher in potential than this above, alright? And this is how we describe it. And consequently, VO2 minus VO1, the difference here between these is 2 times VID over R1 plus VID. Reducing a little bit more, we get the expression that it is VID 1 plus 2R2 divided by R1. Okay? Now with this, okay, with this potential difference here, we can find VO. And observe that this is going to be found by the differential amplifier that we've analyzed in our previous exercises. Then VO will be equal to R4 over R3 times the difference VO2 minus VO1, which is equal to, we simply put this here, and it is R4 over R3, 1 plus 2R2 divided by R1 times VID. Okay? Knowing that VID is this, and to fully describe the output voltage in terms of the input signals, we can write it in this manner. VO is equal to R4 over R3, 1 plus 2R2 divided by R1. VID is VI2 minus VI1. Okay? And this is the output voltage in terms of the input signals. Okay, my friends? Have you fully comprehended what I did here? Firstly, we understood why VID appears across R1. Okay? And secondly, we understood that the current that flows here is the division between the potential difference, the difference between the signals, we are calling this difference VID, divided by R1. And this is the current, okay? And we computed the voltage from here passing along the path of current. VO2 is equal to the voltage drop here, plus the voltage drop here, plus the voltage drop here, plus this voltage here. And we found this expression here that correlates VO2 and VO1 with respect to what we have at this side here, around these two operational amplifiers. And VO2 minus VO1 is the signal, is the output signal of this stage here. It is going to be the input signal of the second stage, but it is the output signal of the first stage. VO2 minus VO1 is this, okay? We have understood this. And now this step here, VO is equal to R4 over R3. Sorry, I made a mistake here. R4 over R3 times this difference here, this difference in voltage. Okay? Observe that all of the resistors here are equal to each other, and whenever this happens, we have that the output voltage is going to be the ratio between R4 and R3 times the difference here, okay? The difference between these two signals that are the output of this stage but the input of the second stage. All right? And now we have described that in this way here. Okay, it moved to here, this moved to here. All right, and now we have fully comprehended what's going on here. Okay, and this is how we understand the circuit here. Okay, this is the first step in understanding this problem. Secondly, we are going to do what the exercise wanted us to do, to replace R1 by a variable resistance. And let's do it. Let's do what the exercise wanted us to do. We are going to assume the strategy of designing the instrumentation amplifier in a way where all the required gain is obtained in the first stage, leaving for the second stage the task of letting pass the difference between the outputs of the first stage and rejecting the common mode signal. That is, the differential gain of the second stage will be only 1. To this aim, we will select all resistors of the second stage to be 10 kilo ohms. R4 will be equal to R3, which will be equal to 10 kilo ohms. Secondly, we are faced with the problem of designing the first stage to realize a gain between 2 and 1000. To accomplish this, we shall replace resistor R1 by the series combination between R1F and R1V, in which R1F is fixed and R1V is variable. Then instead of R1, we are going to use R1F, meaning R1 fixed, and R1V, meaning R1 variable. From the aforementioned theory, we know that VO2, we have just debated this, VO2 minus VO1 is equal to VID 1 plus 2 times R2 over R1. Okay? We have just debated this. We understood this. Okay? VID is the difference between these two signals here. And this difference here, described with respect to this signal, have this parameter here as the gain. Okay? Output written in terms of the input, and the gain is the parameter that correlates these two. In which 1 plus 2R2 over R1 is the differential gain. Replacing R1 by R1F and R1V, we get here, this is the gain. We are going to replace R1 by R1F and R1V. 1 plus 2 times R2, okay? We are taking this step. We are going to replace R1 by R1F plus R1V. And this has to be equal to 2 to 1000. Okay? If we use R1V as 100 kilo ohms, a 100 kilo ohms potentiometer for the variable resistance, we get that the maximum gain occurs, okay? The maximum gain occurs when the denominator is the smallest possible. That is, let me write it here so you guys will be able to understand it better. The maximum gain occurs when R1F plus R1V is equal to R1F. Okay? We cannot vary R1F. R1F is fixed. R1V can be varied. We are going to set R1V to 0, and this is going to give the maximum gain possible. Why? Because the minimum value of the denominator is the one when R1V is 0, and it makes the gain, the entire gain, the maximum. All right? So when R1V is 0, 1 plus 2R2 over R1F is equal to 1000. And now we are going to set R1V to 100 kilo ohms, which is the maximum value that the exercise wanted us to use. And in this way, if we use this big value for R1V, the denominator is going to be big, okay? Then the gain is going to be the minimum. 1 plus 2R2 divided by R1F plus 100 kilo ohms is equal to 2. Okay, now we have a system of equations. Okay, we have to find a solution for this system of equations. This is the last step in solving this exercise. Solving this system, we find that R1F is equal to 100.2 ohms, R2 is equal to 50.05 ohms, and among commercially available resistors, we may select. These are not available in the market, okay? These are the exact values, the perfect solution, but the real world is not perfect. We are not gonna find these values of resistors in the market. We need to adjust our systems to what the market offers. So we are going to use, instead, we are going to use R1F equal to 100 ohms, R2 equal to 50 kilo ohms. Here's kilo ohms, and R3 will be equal to R4. We have already said that 10 kilo ohms, okay? And the potentiometer that we're going to use for the place of R1 for R1V is 0 to 100 kilo ohms, okay? And in this way, using this R1F 100 ohms, R1V is here, 0 to 100 kilo ohms. R2, this to R2 is 50 kilo ohms, and R3 equal to R4 equal to 10 kilo ohms. In this way, we can construct an amplifier whose gain vary from 2 to 1,000. Okay, my friends, this is the exercise, the last exercise number 7, and this is the video that I wanted to make addressing operational amplifiers, and I hope you enjoyed it and learned from the video. I'm a teacher, guys. If you want to book a lesson with me, use my WhatsApp number. Goodbye!